So.
Phil.
Yeah.
Ready?
Yeah.
We could hear?
Yes.
Okay. Siva?
Yeah.
Talking about just.
Yeah.
Sophie said that you should not, because everyone will go today due to the
Okay, we can see.
to the early lockdown.
Okay, but my friends are there, so anyways, there are at least 2 or 3 we will order and we will eat. Whoever is there. So this try to open?
Yes.
Okay.
Yes.
Girls?
How would you
like to learn?
The description. Yeah. But I said that il lit croissant, il lit Halloween de Corée, et après les petits pains.
Okay.
Like this? Yes, like that.
Okay.
Demi-cercle.
We're learning anything?
How you grab so many feet?
For us, we just eat from the box.
Yeah.
And then. Yes.
So that there or?
I think one way it will be. They will just come and take. Maybe. But now I'm thinking we can give them the. You know? Sure, yes. The video. But we took the plate or not?
We took this plate, the three
box.
We took the box and the plate.
And the plate with this.
Yes, I think that we can give them the plate.
Yeah. Plates in the plates?
Yes.
Okay.
Généralement, ils ne mangent pas pendant la...
Parce que comme c'est pas very good.
Ouais, c'est juste...
Usually they do not eat, but since due to the COVID.
But here we have difference, we give.
The same in Nigeria. In Nigeria we give like in box.
Yes, we do.
But after...
No?
C'est
No, they do.
Okay.
Yes.
So it's good to have the ventre plan.
And not being occupied by the presentation. And this we just keep it like this.
Yes.
Voilà comment la cuisine mais it is not finished, we have to put it right for a day. So we need to put this one.
Yes.
There
Just here?
Yes.
So how do you feel?
Did you?
How do you feel?
Just like that.
Did you have lunch?
Yeah.
You got? You could?
For fun.
If you could eat, that's good.
Even for no.
Not for coffee, but for water. For coffee, we give in a small cup. The coffee is not yet there.
Not yet ready. We will wait 5 minutes more. So that at least 5-6 cup coffee will be there.
Exactly. You want to give the nuts as well? Yeah.
And see.
We had more things for this plate, no? Yesterday, chips.
Chips will.
Yeah, you want to keep it for later.
Chips not. There are mostly, but mostly and chips is not.
Okay.
But if I want to put them on the shelf. This is spicy. Huh?
Not this?
No, without this.
Happy birthday.
Yeah.
Tu dois arrêter.
Après, non.
Sûrement.
Ah ouais.
Surtout au dernier moment. La dernière minute déjà.
So they are coming. They are coming.
Hello.
Bonjour.
Donc Pierre, il va nous donner le temps de phase.
Léa, moi,
I came this morning actually because I wanted to measure a student for the hearts. He was sick this morning, so actually he couldn't come. So. Là, c'est Jean-Pierre qui ont fait tout le
J'ai pas pris les infos.
quite right, because I arrived at 11, so I did stop then I received
Ça va, ça fait longtemps que c'est pas vu.
Bah oui, quand même, trop longtemps.
Bah oui, tu fais quand on passe. Quand on passe à CSL, je connais, t'es pas en fait.
Yeah, this is the morning. It was raining, so it was
Ouais, ça aurait été sympa, effectivement, qu'on passe juste à la
so nobody wished that the results after this. Oh yeah, I really hope so. I will respect that.
J'ai vu qu'il répondra assez rapidement, on le voit pas souvent.
And today I will come back to the Valisex. Oh, Daniel told me he should finish today. So I told him that it was
Ouais, parce que t'as des manies, c'est ça.
C'était très obligatoire. Donc, il y en a qui s'en foutent, mais normalement, tu es très $6 capable de se mettre chez toi.
Yeah, it's very similar.
Je fonctionne à une semaine au CSL à l'année.
It's going to be recorded.
Les cours, c'est par exemple, à distance. L'ordinateur, tu vas t'en
Yes, it's going to be question, it's pas that.
So other like this for
Ah ouais, c'est vrai.
All right.
Pardon, vas-y.
Ah, great. Fantastic.
Bon, je me mets en
Is everything right?
Bonjour, ça va bien? Enchanté. You are the candidate? Yes.
Please,
It's fine. It's okay. No stress. You have no stress. You have no stress? For the moment, I non, c'est ça, exactement.
C'est bien.
Donc, faut s'asseoir là où il y a des verres, il paraît, non? Parce que c'est une place sur deux. Je sais pas comment c'est une place sur deux, je vois pas. D'un coup, le premier s'installe, c'est comme ça, on verra comment ça se passe.
Oui, une place sur deux.
Voilà, c'est la blague. Il n'y a pas le pied, justement. Faites attention, prenez-le, il n'y a pas le pied, sinon ça fait mal. Tu as fait escale à l'île, Serge? Tu étais revoir ton hôtel habituel, non?
Non, je ne loge pas, je suis...
Non, je sais bien, mais tu as déposé ta femme là à côté, je suppose.
Non, mais je me suis garé au parking de Villeflore pour avoir facile. Moi, je suis venu en...
Ah oui,
métro,
d'accord, ok.
Et donc, je me balade un peu en ville tout à l'heure. On se donne rendez-vous à la gare de Villeflore pour repartir. On a eu un temps avec les écrans pour venir.
Mais oui, mais c'est ce que j'ai dit, j'ai pensé à toi, parce que ce matin, tu as un temps pourri, mais cet après-midi, il va y avoir beau temps pour les magasins. Est-ce que c'est pas le principal?
Je ne sais pas si c'est le principal, je ne sais pas comment il faut.
Mais moi...
Il est très mauvais, parce qu'il est enfermé à un seul endroit, ne bouge pas.
Ouais, c'est ça, ouais, c'est vrai, c'est vrai. Mais ce matin, j'ai vu ça, je lui ai dit, mon Dieu, il est très très mauvais ce matin, il fera pause cet après-midi.
Tout le monde veut un café?
Moi, je veux bien, ouais.
Oui, moi je veux bien aussi, oui, s'il vous plaît, oui.
Ça vous... Sorry?
Ouais, je veux bien, ouais.
Je suppose
Tu l'as
que...
goûté?
Non.
Bon, s'il est fort, tant pis pour toi.
So,
Pardon.
Il y avait des pizzas là-bas. Nice meeting you.
Nice meeting you.
No problem.
Thank you.
so
Et de la notice.
Okay. You go across here and you take to the next one.
Yes. Thank you.
Je donne le reçu.
Merci.
Bon, merci.
Sorry, thank you.
Ouais, non, pas besoin.
Ah, c'est bon. T'as le temps.
Moi, je ne veux pas de sucre, merci.
Ah, d'accord.
Il a l'air fort, hein.
Vous voulez du chou?
Non, merci. Non, merci.
D'accord.
Non, ça va, ça va. C'est bon,
C'est bon.
j'ai bien ce
Bien.
qu'il faut. Ouais, ça va.
Ah oui, c'est...
Oh, non, parce que ça va être café, ça va trop bien, ça.
Merci.
Bon, ça ira, merci, je sais pas, moi, vous avez bien démontré.
Non, il est à la règle sanitaire, si ça doit être classé à distance, on doit avoir du masque, on le garde. Il est à la règle.
Je pense.
Alors, les règles sanitaires, je ne sais pas, au nom du président de jury, ça tombe bien.
Mais on va ici, justement,
Non, a priori, on enlève le masque quand on mange, quoi, mais bon. Je sais pas, hein, parce qu'on fait quoi, c'est quoi qui ont mis les règles? On a le droit d'enlever le masque comme on les doit ou pas? Non, hein. Sur le principe, non, il ne faut pas l'enlever, sur le principe.
Non, sinon, les cas compacts, si jamais quelqu'un est... Ah ouais, c'est embêtant.
Par contre, on le sait d'aller, on ne sait pas du tout.
Voilà.
Oui, oui, c'est tout à fait autre chose qu'on peut aller aussi.
Donc on doit effectivement se réunir sur les idées du président du jury. Ça peut pas être les encadrants, ça peut être le professeur d'université, généralement l'équivalent. On n'impose pas au rapporteur qui a déjà fait un rapport, de refaire un rapport à la suite. Donc vu la composition du jury, il y a une seule personne qui peut... Donc si vous en êtes d'accord, on désigne Toami comme président. S'il y a des objections, comme on dit dans les mariages, c'est maintenant et jamais. Pas maintenant, qui se jamais. Ok, là, merci.
Voici d'assumer son rôle inédit dans cette configuration.
En tout cas, merci quand même d'être tous là présents, parce que c'est quand même rare en ces moments d'avoir un jury entièrement présentiel. Donc merci d'avoir fait le déplacement.
Si vous le souhaitez, on peut peut-être se faire passer la bouteille d'alcool. Ça faut se partager ça pour nous. Tous.
Vous êtes d'accord. Ça rappelle de mon souvenir, mais. C'est pas exactement la même chose. On a déjà vécu ça autrement.
C'était un clin d'œil au passé.
Oui, exactement.
On peut le faire en fait.
Oui, oui.
Thank you. Merci.
This the teacher is okay. So it's right. Yeah. Yes.
Yes, yes.
So, hello Mr. Ganison, and hello to all of those who will be following the presentation behind the computer. You present today synthesis of the work you carried out in your doctoral thesis, entitled Surface Plasmon Resonance-Based Biosensor Applied to Photosanitary Medicine, to obtain the degree of the doctoral degree of the University of Lille. And you will have about 45 minutes to present the main result of the research. But before you begin to present your work, I would like to introduce the committee members. And first of all, I will begin with the reviewers of your manuscript. So Professor Serge Abrakan from the University of Liège, Professor Gilles Lerondev from the Technical University of Troyes, on the right side. So Fabien Doctu, engineer in the company Multitel, and the supervisors of your work, so Sophie Marico, associate professor at the University of Lille, and Jean-Pierre Vico, CNRS research director here at Erlangen, and myself, Tomias Louis, professor at the University of Lille. So now the floor is yours, and we listen to you.
Thank you so much. Good afternoon to one of our present here, and thank you so much for your introduction. The goal of my PhD work, which is also in the framework of the project, is to develop a portable surface plasmon resonance-based biosensing tool to detect Xenoseptoria critici and Candida albicans. Let us see what is Xenoseptoria critici and Candida albicans. The image shown here is the disease-affected wheat crop, which is called as Xenoseptoria critici. On the right is a SEM image of a human pathogenic yeast, which is called as Candida albicans. The Xenoseptoria critici is a wheat plant pathogen that can cause septorial leaf blot, as shown in the red circle. And this pathogen can reduce the yield of wheat by 30 to 50%, which can cause a huge economic impact. And this pathogen is very difficult to control as they are resistant to multiple fungicides, and their pathogen, their population has high number of genetic variabilities, and also their biology has very unusual biology, and it's as a pathogen. On the other hand, Candida albicans is a human pathogenic yeast that is present in the human gut flora, which is in the digestive tract of the human body. Many people get infections due to the infection that is caused by Candida albicans. Mortality rate of 40% has been reported due to the infections caused by Candida albicans. And the symptoms of Candida albicans can be seen on the skin, genitals, throat, mouth, etc. For this, we need to detect these pathogens before they show their symptoms. For that purpose, we need to use a biosensing tool that can be applied in the field of in agriculture and also in the medical domain. A biosensing tool is a combination of all these. It has a sensor, biorecognition element, reading equipment, and data processing. A sensor and biorecognition element itself is a biosensor, where it can transduce a biological interaction into a measurable signal. And to convert this measurable signal into a user-readable value, we need to use a reading equipment combined with data processing. All these elements integrated together is a biosensing tool. Each element of this tool has to be developed by a specialist in their field. This project is funded by the European Union called Interact Smart Biocontrol Biosense, where each element of the tool is developed by a specialist. They are one of our project partners. The sensor is developed at Material Nova, CSL, and IEMN. The biorecognition element is developed at CARA and CHU, a hospital in Lille. The CHU, they extract DNA from Xenoceptoria to be functionalized on the sensor surface. CHU, they extract antibody from the pathogen Xenoceptoria as well as from the Candida albicans to be functionalized on the sensor surface. And the reading equipment is developed at CSL, IEMN, and also by Multicell. The data processing is shared between IEMN and Multicell. At the end, integration of all these elements are developed at Multicell. During my PhD, I worked on developing the reading equipment and also the sensor of this tool. My thesis work I have divided into 4 different parts, where in the first part I will introduce a brief history of surface plasmon resonance, the theory, their techniques, and their working principles. In the second part, I have worked on the development of the sensor and also the reading equipment, where modeling and experiments has been performed in angular interrogation and spectral interrogation scheme using 2 different sensors, gold and silver gold. In part 3, I have addressed on the cost of the portable system. For that purpose, I worked on the fabrication of polymer-based optics, where polymer-based plasmonic tape sensor and polymer coupling optics, a PDMS prism, has been fabricated and will be discussed. In part 4, I worked on the temperature controlling of this tool for the modulation of the temperature of the SPR sensor, supported by modeling and experiments, and the technique to control the temperature will be discussed. And at the end, the conclusion of all the 3 parts will be again concluded under the heading overall conclusion. Let's go into the theory of surface plasmon resonance. The surface plasmon resonance phenomena was first observed by Romans in 4th centuries. Here shown is the leukocyte curve, which appears to be green in color, but after it starts the color, once a light source is placed inside this curve, the color starts to vary. And this is because there is a secret ingredient present inside this curve, which is called as metallic nanoparticles. These metallic nanoparticles, when they are resonant condition, they exhibit various wavelengths of light. This is the reason the color of the light is varying depending on the point of view and the time of the day. The surface plasmon resonance are of 2 varieties. They are localized surface plasmon resonance and propagated surface plasmon resonance. The localized surface plasmon resonance are developed by 2 of our project partners, Material Nova and CSL. I work on the propagated surface plasmon resonance. What are surface plasmons and how they can be in resonance condition? Surface plasmons are free electron oscillation that exist between 2 materials, a metal and a dielectric medium. And the metal can be few tens of nanometers. This oscillation can be imaged as evanescent wave. And this wave can penetrate both into the metal as well as dielectric medium. And the penetration depends on the physical properties of both the materials, that is, dielectric permittivity. And this plasmonic wave does not exist spontaneously. One has to use external energy to excite them. For that reason, we could use photons to excite the surface plasmons. But a light in free space can excite surface plasmons. Here shown is the dispersion relation of the light propagating in the free space given by x component of the wave vector k naught sin theta, and the red line is the dispersion relation of the plasmonic wave which is present at the metal dielectric interface. We could see that the dispersion relation of the light propagating in the free space does not intersect with the plasmonic wave. It means that the plasmonic wave cannot be excited by a light which is propagating in free space. To excite them, we need to make the propagation constant of the light propagating in the free space matching with the propagation constant of the plasmonic wave. To match them, one has to use excitation schemes. So by using the excitation scheme, there are two different methods to couple the plasmonic wave. Either by using diffraction grating or by using attenuated total reflection. By using diffraction grating, the periodic correlation in the metal surface can diffract the light into the plane of metal dielectric interface, resulting in the resonant coupling of the plasmonic wave with the incident light. By attenuated total reflection, they can be applied to two different configurations. They are Otto's configuration and Fresnel configuration. In Otto's configuration, there is a gap between the metal and the prism surface. In Fresnel configuration, a metal is directly deposited on the prism surface. The Otto's configuration is commonly used to study solid phase medium, and Fresnel configuration is used to study liquid phase medium. So we use Fresnel configuration in this part. Let us see again the dispersion relation of the light which propagates through the prism, which is now given as the x component of the wave vector is given as k naught np sin theta, where we could see that the light propagating in the prism can intersect at one point of the plasmonic wave, and this point is the resonant condition, and the propagation constant now becomes as shown here. It depends on the wavelength of the light that is used and the refractive index of the prism and the angle of incidence. They also depend on the permittivity of the dielectric medium and permittivity of the metal. So if we change the refractive index of the prism, obviously the propagation constant of the light will be changing, and once if it is changing, there will be another possible excitation scheme where the resonance condition would be here as shown. By using this configuration, there are two different interrogation techniques, that is intensity interrogation and phase interrogation. During my work, I work only on the intensity interrogation, and the intensity interrogation has two different schemes. It has angular interrogation scheme and spectral interrogation scheme. Let us look on the working principles of both the interrogation schemes. In the angular interrogation scheme, we use Fresnel configuration, where a metal is directly deposited on the prism surface and a monochromatic light source is used to incident on the surface of the metal. And this light has various angles, and the reflected light from the surface of the metal is directed to a detector, and the incident light is tuned, the angle of incidence of light is tuned till we achieve the plasmon resonance condition at the metal dielectric interface. Once the resonance condition is obtained, we could see a loss in the intensity in the reflected light beam, which is as shown here. And this angle is known as resonance angle. Once the refractive index at the sensor surface is varied, let's say we add a drop of water, we could see a shift in the angle, and this shift in the angle is due to the change in the refractive index at the sensor surface, which is given as sensitivity. And this sensitivity is an important parameter to understand the plasmonic sensor performance characteristics. And the detection of the refractive index at the surface is limited to the penetration of the evanescent wave as shown here. In the spectral interrogation scheme, we use the Fresnel configuration. Instead of using monochromatic light source, we use a polychromatic light source where it has various wavelengths, and the angle of incidence is fixed, and one of the wavelength from the source will excite the surface plasma waves. And the reflected light is directed to a spectrometer, and we could see a loss in the wavelength in the reflected light beam. This corresponds to the coupling of plasmonic wave at the sensor surface. once the refractive index at the sensor surface is varied, we could see a shift in the wavelength, the absorption wavelength, and this shift in the wavelength is because of the change in the refractive index at the sensor surface, which is given as sensitivity. And the detection or the limit of detection is depending on it, limited to the penetration depth as seen here. So what is the difference between angular interrogation and spectral interrogation scheme? In angular interrogation scheme, we use monochromatic light source, and the angle of incidence is varied to couple the plasmonic wave, and the camera can be used as a detector. In spectral interrogation scheme, we use polychromatic light source, and one of the wavelength from the light couples the plasmonic wave, and the angle is fixed. A detector can be a spectrometer. So, understanding the theory, modeling has been made as the first modeling was done to understand the influence of prism material. For that purpose, we changed the refractive index of the prism and calculated the shift in the resonance angle at various wavelengths as shown here. Here, the permittivity of the dielectric medium is considered as water, as it is equivalent to the biological liquid solutions. We could see we use two different materials of prism, HZF1 and BK7. The HZF1 has a higher refractive index, and BK7 have a lower refractive index compared to HZF1. And by using this, we could see that the resonance angle by using higher refractive index prism is lower, and the resonance angle is higher for using lower refractive index prism. We have chosen to use HZF1 material as prism, as it is giving lower resonance angle, and which is easier for us to develop the optical setup. Further modeling has been performed to understand the influence of the plasmonic layer thickness. Here, the plasmonic layer is considered as gold, and in the angular interrogation scheme, we use the wavelength is fixed, and the thickness of the metal was varied, and the plasmonic response has been recorded as shown here. We could see for the thickness from 25 nanometers to 50 nanometers, the full width half maximum of the plasmonic peak reduces, and by increasing more than 55 nanometers to 85 nanometers, the full width half maximum is constant, but the contrast starts to reduce. By increasing more than 85 nanometers to 100 nanometers, the plasmonic minimum peak starts to disappear. It becomes more reflective. To see that, when we increase the thickness of the plasmonic layer, the resonance angle is decreasing, and the contrast of the plasmonic peak or the plasmonic curve is reducing when we use the thickness more than 55 nanometers. And the plasmonic minimum peak starts to be more reflective when the thickness of the plasmonic layer is chosen to be more than 85 nanometer thickness. So, the sensitivity was calculated for various thickness of the plasmonic layer in the angular interrogation scheme. And the sensitivity in this scheme is given as change in the resonance angle due to the change in the refractive index at the sensor surface. And this change in the refractive index we have considered as various concentrations of ethylene glycol, as it would be used in our experimental purpose. And the calculated sensitivity for various thickness of metal, gold, is as shown here. We could see that the sensitivity is almost constant for whatever the thickness that is used from 20 to 65 nanometers. But we have a higher sensitivity peak, which is at 75 nanometer thickness of the plasmonic layer, but we saw that the contrast of the plasmonic layer was reducing at the higher thickness of the metal. So we could see the calculated sensitivity is around 65 plus or minus 3 degrees per RL. The sensitivity calculation was also performed by using bimetallic layer silver gold, and the calculated sensitivity is as shown here. And this sensitivity was calculated for various combination thickness of silver gold, and we could see that the sensitivity that was calculated by using bimetallic layer is almost giving the same, it is in the same range of all the combination thickness of silver gold. When we compare the sensitivity that was calculated by using gold and silver gold, we could see that the sensitivity that was calculated by using gold metallic layer is shown in the two limits of red line, And when we compare, we could see either by using gold or by using bimetallic layer, the sensitivity is almost in the same range. Further, modeling was also performed in the spectral interrogation scheme, where the influence of the plasmonic layer thickness was calculated, and here the resonance angle is fixed and absorption in the wavelength for various thickness of the metal has been recorded as shown here. We could see by the full width half maximum of the plasmonic peak reduces when the thickness of the plasmonic layer increases. Further, the sensitivity was calculated for various thickness of the metallic layer, and the sensitivity in the spectral interrogation scheme is changed in the wavelength due to the change in the refractive index at the sensor surface. And the calculated sensitivity for various thickness of the metal, gold, is shown here. We could see the sensitivity is higher by using the plasmonic layer of thickness 30 to 35 nanometers, but after the sensitivity decreases for the higher thickness of the plasmonic layer. Here is gold. Further, in conclusion, the modeling has been performed in sensor level, angular interrogation and spectral interrogation were performed, and the modeling was performed by using two different sensors, gold and silver gold, where the thickness of the gold and the thickness of the bimetallic layer silver gold has been modeled based on the performance characteristics of the sensor. Further, we used this parameter to fabricate the sensor either for gold or bimetallic layer to be giving a higher performance. And further, going to the experimental part, the first experimental setup was developed in the angular interrogation scheme as shown here. The angular interrogation scheme was already existing in the laboratory, but this system was optimized during my PhD work, where it has a polychromatic light or monochromatic light source which is working at 1550 nanometers, and the light is made to pass through a polarizer and couple of lenses, and it is reflected to the prism surface, and the reflected light from the prism is directed to a camera, which is here we use an infrared camera. The mirror is mounted on a micro-rotating stage where we could tune the incidence angle to the prism finely. Further, the box shown in the red is the fluidic device where fluids can be introduced for the measurements. First, we measured the sensitivity of the system by using the tool. The sensitivity for 35 nanometer thickness of plasmonic layer was measured, where the sensitivity as shown here changed in the resonance angle due to the change in the refractive index at the sensor surface for various concentrations of ethylene glycol is shown. We also compared the measured sensitivity with the theory, and we could see that both are in good agreement, and the measured sensitivity by using gold as plasmonic layer is as shown. The sensitivity was also measured by using bimetallic layer silver gold, and we compared the measured sensitivity measured by silver gold that is shown in the red with the sensitivity that was measured by gold, which is shown in the black. We could see that the sensitivity measured by gold and silver gold, and there is a slightly improvement in the sensitivity that was measured by silver gold compared to gold sensitivity. Further, the optical setup in the spectral interrogation scheme was fully developed during my PhD work, where this setup has a polychromatic light source which is incident or passing through a polarizer and a plane of convex lens, and it is reflected through a prism, and it is directed to a collimator which is connected to a spectrometer. And this red box is the place where we use a fluidic device to introduce various concentrations for the measurement. And the sensitivity was measured for two sensors by using this optical setup. The sensitivity that was measured by using 35 nanometer plasmonic sensor is as shown here. The change in the wavelength due to the change in the refractive index at the sensor surface for various concentrations of ethylene glycol is as shown here. The sensitivity that was measured was also compared with the sensitivity that was calculated, as can be seen. We could see that both has good agreement, and the measured sensitivity is as shown. The sensitivity was also measured by using bimetallic layer silver gold, and the measured sensitivity which is shown for silver gold is in red, and the measured sensitivity of silver gold was compared with the sensitivity that was measured by gold sensor. We could see that in the spectral interrogation scheme, the sensitivity is also higher for using silver gold compared to gold, but the improvement in the sensitivity is very slightly higher. In conclusion, the experiments were performed on both the interrogation schemes, angular and spectral interrogation scheme, and the angular interrogation scheme was already, optical setup was already existing, and I optimized this setup during my PhD work, and it was calibrated by using two different sensors, gold and silver gold. The spectral interrogation scheme was completely developed during my PhD work, and it was also calibrated by using gold and silver gold. The sensitivity was measured in both by using two sensors in both the interrogation schemes, and the measured sensitivity is as shown in the table. We could see that the sensitivity that was measured by using silver gold is 5% higher compared to the sensitivity that was measured by gold in the angular interrogation scheme. When we see in the spectral interrogation scheme, we could also see the sensitivity by using silver gold is 20% higher compared to the sensitivity that was measured by using gold sensor. But when we see, we also evaluated the minimum limit of detection from the noise that was measured from the optical system during the measurement, and the evaluated minimum limit of detection is shown here for two sensors in the two interrogation schemes. We could see the minimum limit of detection is better for gold in both the interrogation schemes compared to silver gold. Further, addressing on the cost of the portable system, I worked on the development of polymer optics, where polymer-based plasmonic tape sensor was fabricated, and PDMS prism, a PDMS sensor was fabricated, and polymer-based coupling optics was worked, and PDMS prism was fabricated as shown here. The sensitivity was measured by using tape sensor, and for that purpose, we stick directly the tape sensor that was fabricated on a glass prism here, which is the glass prism is HZF1, and we measured the sensitivity, and this sensitivity was measured in the angular interrogation scheme. So the change in the resonance angle due to the change in the refractive index at the sensor surface for various concentrations of ethylene glycol is as shown. The black is the sensitivity that was measured by the tape sensor, and the red one is the sensitivity that was measured by the glass sensor. We could see when we compared the measured sensitivity by using tape and the glass sensor, we could see the sensitivity is slightly lower, that is 20% lower sensitivity by using tape sensor compared to glass sensor. The PDMS prism was used, and we measured air plasmon and water plasmon in the spectral interrogation scheme for various combinations of sensors with PDMS prism. So the first PDMS prism was coupled with a glass sensor, and the air plasmon was measured. We could see it has a good signal to noise ratio. But when we measure the water plasmon, the plasmon can be seen, but the signal to noise ratio is poor. By using the combination of PDMS prism and PDMS sensor, we could see the air plasmon was measurable, but the water plasmon was not possible to measure. By using the combination of PDMS prism and the tape sensor, the air plasmon was measured. The water plasmon also can be measured, but we could see a huge optical interference in the signal, which can be due to the tape was not stuck properly on the prism surface. And at the end of the talk, we could also see the experimentally made PDMS prism and the combinations of sensors. In conclusion, in order to work or in order to address the cost of the portable tool, I worked on the polymer optics, where polymer-based plasmonic tape sensor was fabricated. The advantage of this sensor is that it can be cut into any size and any shape, and can be directly stuck on the prism without using matching index oil. And the output of water plasmon with the tape sensor is as shown here, the water plasmon and its profile. and the sensitivity was also measured by using the tape sensor, which was also compared with the sensitivity that was measured by glass sensor, which is shown in the box. We could see that the sensitivity of tape sensor is 20% smaller than the sensitivity that was measured by the glass sensor. But the sensitivity could be improved by using higher quality tape substrate. In the polymer-based coupling optics, PDMS prism was fabricated and the air plasmon was measured, and when we compared the air plasmon that was measured by glass prism, which is shown in the black, we could see the signal to noise ratio of the plasmon which was measured by using PDMS prism gave a good signal to noise ratio compared to the plasmon that was measured by glass prism. It can be viewed that when by using the glass prism, we use matching index oil, and if the matching of the sensor on the surface of the prism is not good, we could see the loss in the intensity as shown here. But when we wanted to measure the water plasmon, we could see that the water plasmon by using PDMS prism gave a poor signal compared to the glass prism. It can be viewed that the refractive index of prism is lower, and the angle of incidence to couple the plasmon in the experimental bench is almost horizontal to the surface of the prism. That is the reason it is not possible for us to measure the water plasmon. But this can be improved by using higher refractive index polymer materials. Further, to control the temperature of the portable system, the main question is where to maintain the temperature of the plasmonic sensor. Here shown is the animation which was said that the sensing area is limited to the penetration of the fluorescent wave as shown here. And this penetration depends on the wavelength of light that we use. And the calculated penetration depth for various wavelengths is as shown here, which is calculated for plasmonic layer gold of 35 nanometers. And we could see that the penetration of the fluorescent wave is maximum 1.3 micron by using higher wavelengths. So the idea is to maintain the temperature at the close vicinity of the sensor surface. How to heat the plasmonic sensor? So here is the classical plasmonic sensor, which is fully metallized, and it has facilitated with 4 channels of microfluidic device, which is used for the biosensing applications. If we wanted to heat this fully metallized sensor, we need to use a bulky heating system, and this can heat a sensor substrate completely. But our idea is to use Joule's heating effect for the plasmonic sensor. For that purpose, a special design was performed and fabricated as shown here. We have 4-channel plasmonic sensor, and it can be facilitated with microfluidics of 4-channel. At the same time, the plasmonic sensor can be used as a Joule heater by injecting current. The conductivity of the fabricated sensor was measured at various temperatures, and the 4-channel sensor was modeled using console multiphysics as shown here. So this is the modeling was performed by taking into account various parameters of glass and gold. Here, the density, thermal conductivity, and heat capacity for glass and gold was considered for this values, and the electrical conductivity for gold was varying, which was taken from the previous measurement values that was shown. The glass used here is HZF1 material, and gold is around 35 nanometers, which is our plasmonic layer. Further, a small area on one of the channels was delineated as shown in the white box in order to reduce the rendering time of the software, and the temperature rise across the channel was calculated for various injected current. And the cross section is shown here. The temperature rise across the channel width for various injected current is calculated as shown. From this, we know what is the temperature, what is the current that has to be injected to the plasmonic sensor to have particular temperature rise. Further, the 4-channel sensor was carried to the thermal camera, where it has a thermal infrared detector, and the substrate folder can be maintained at particular temperature and we use current probes to inject current through the channel of the sensor. When we take a closer look on the sensor, we could see that we have deposited a thin film of cathode on the surface of the sensor, and this is because in order to improve the infrared radiation of gold, we could see as the thermal image from the thermal camera, we could measure the temperature rise where there is a film of cathode, but where there is no cathode, we could not measure the temperature rise. The modeling was performed to understand the influence of the cathode film on the surface of the metal on the sensor, and we verified that using a thin layer of cathode on the surface of the sensor does not influence the thermal measurements. Further, the cross section was taken and the temperature rise across the channel was measured and was compared with the modeling that was done earlier. We could see that the modeling is shown in the dotted line, and the experiment that was performed by thermal camera, which is shown in the solid line, we could see that the temperature rise, they have good agreement between the experiment and the modeling. From this experiment, we validated the Joule's heating effect, where for the injected current versus temperature rise. And the temperature rise here was considered as the peak temperature rise at the center of the channel, which is shown in the black dots. By using this technique, Joule's heating technique, we could also maintain the temperature of two different channels at the same time. Here is an example that we injected the current in two of the channels, and we could maintain two different temperatures at the same time. And we could see that the temperature difference between two channels is around 0.5 degrees. As an example, also we could see that we could maintain 1.2 degrees between two channels. So the advantage of this technique is that we could heat or maintain the temperature of two channels, and small temperature difference on the two channels can be maintained at the same time without any crosstalk. When we inject high current, we measure higher temperature in one of the channel, but we could see a small negligible changes in the channel where there is no current flow. Further, we wanted to measure the refractive index of water at various temperatures. For that purpose, we used the spectral interrogation scheme was upgraded for this experiment, where we used the 4-channel sensor, and current probes were used to inject current through one of the plasmonic channel, and a drop of water was heated by injecting current through the channel. And by theory, we know the refractive index of water at various temperatures, which is shown in the orange line. And this is the measured refractive index of water at various temperatures, which is shown in the blue line. We could see that there is a discrepancy between the measured refractive index of water with the experiment and the theory. This is because we took the temperature rise, which is the peak temperature rise at the center of the channel, which is in the blue. But instead of taking the peak or maximum temperature rise at the center of the channel, if we take the average temperature rise, that is average temperature across the channel, we could see that the experiment is matching, which is shown in the yellow. We could see that the experiment matches with the theory far better compared to taking the peak value. Further, to control the temperature of the channels, we have also fabricated a platinum resistor on multiple channels to control their temperature at the same time. And the fabricated platinum resistor was calibrated, where the temperature, the resistance of the platinum that was fabricated was measured at various temperatures. From this measurement, we measured the temperature resistance coefficient of the fabricated platinum, which is around 3.2 10 to the power minus 3 ohms per degree Celsius. Once the platinum was fabricated on the 4-channel sensor, this was taken under the thermal camera, where one of the channel was injected current, and the temperature rise was measured by the thermal camera, and also the temperature was measured by using the help of platinum resistor. As a result, we could see that the temperature measured by the thermal camera, which is shown in the black solid line, and the orange line is the temperature that was measured with the help of the platinum resistor. They have a discrepancy at the higher injected current or higher temperatures. But we did the same as we did before. Instead of taking the peak temperature value of the thermal camera, we took the average temperature across the channel. When we take the average temperature across the channel, which is shown in the gray line, we could see that both are in good agreement. The temperature that was measured by the thermal camera, which is shown in the gray, and the temperature that was measured by the platinum resistor, which is shown in the orange. Both are in good agreement. In conclusion, to maintain the temperature of the biosensing tool, to moderate the temperature of the sensor, a specific design was fabricated as shown here, which has 4 channels, and Joule's heating effect has been validated. For particular injected current, what is the temperature rise should be across the channel. And it was also seen that the 2 channels can be heated at the same time and small temperature difference can be maintained at the same time. Further, to control the temperature of the channels, platinum resistor was fabricated on 4 different channels as shown here to control the temperature. Then, going on to the overall conclusion of my PhD work, where I worked on developing the reading equipment and also the sensor. The experiment and modeling has been performed in 2 interrogation schemes, angular and spectral interrogation scheme, by using 2 different sensors, gold and silver gold. By using this sensor, the sensitivity was measured for the 2 sensors in the 2 interrogation schemes, and the measured sensitivity is as shown in the box. We could see that the sensitivity can be slightly higher by using silver gold in both the interrogation schemes, but the sensitivity rise is around 5% in angular interrogation scheme, and in the spectral interrogation scheme we could improve 10%. But there is not big difference in the sensitivity either by using gold or silver gold. To address the cost of the portable system, I worked on the development of polymer optics, where polymer-based plasmonic tape sensor was fabricated. The advantage of this sensor is that it can be cut into any size or shape to be directly struck on the prism without using matching index liquid oil. And the sensitivity was also measured by the tape sensor, and it was compared with the sensitivity that was measured by the glass sensor. We could see that the sensitivity measured by the tape sensor has 20% lower sensitivity compared to the sensitivity that was measured by the glass sensor. But this sensitivity can be improved by using a high quality tape substrate. And we could also see that a 4-channel sensor has been fabricated in the tape sensor. Going to the coupling optics, PDMS prism was fabricated, and the water plasmon was not possible to measure by using PDMS prism. And it can be viewed that it can be improved by using higher refractive index polymer materials. To control the temperature of the portable system, a special design plasmonic sensor was fabricated, where it has 4-channel sensor, and the Joule's heating effect was validated. And it was seen that 2-channel sensor can be heated at the same time, and small temperature difference can be maintained at the same time. And to control the temperature of the plasmonic channels, platinum resistor was fabricated on the 4 channels to control individually the temperature on 4 channels. As a perspective of this work, we could, as said in the first slide, our aim was to develop a portable biosensing tool, where this is the tool that was developed during the project, which was developed at Multitel. When we take a closer look of this tool uses spectral interrogation scheme. They use polychromatic light source, which is passing through various lenses, and they use a glass prism and coupled with the 4-channel sensor that was fabricated in AML. And the signal, the reflected signal from the 4-channel sensor is connected to 4 collimators that is connected to a 4-channel spectrometer, which was developed at Multitel. And the Multitel also worked on the data processing, and we could see on the screen that the plasmon that was measured on the 3-channel is as shown. But this portable system does not include the temperature control for the moment. So this system can be introduced with the 4-channel sensor that can be heated by injecting current, and the temperature can also be controlled by using the platinum resistor that is fabricated in the sensor. So if they use this kind of sensor, they could maintain the temperature of 4 channels at the same time. And it is also given with the classical USB connectors so that it is easier to be adapted in a portable system. Then the modeling can be performed to understand the influence of current flow through the plasmonic channel on the plasmonic curve. This system can also use polymer optics, where polymer-based PDMS prism can be used, and plasmonic tape sensor can be used in order to reduce the cost of the portable system. So, coming to the end, I thank both of my supervisors. I especially thank Laurent Hay, who worked on the data processing in our lab and supported during my PhD work. I thank Jean-Mohamed Tayyeb Bakouchi, who worked on the functionalization of the sensor surface, and I thank Jean-François Robilot for giving support in the console modeling. I also thank all the members from the thermal characterization room and the people from clean room, and I thank the mechanicians who was supporting during the building of the optical setup. I thank the University of Lille for providing the funding for my PhD work. I thank the project Interact and all the partners of the project. At the end, I also thank my parents and my brother for supporting during my journey. At the end, thank you so much. Merci pour votre attention. Thank you.
Thank you, Mr. Gessin, for this very dynamic presentation. So we go now to the discussion, and this is the tradition to begin the discussion with the reviewer of work. So I give the word to Serge Brian, maybe first one who will ask question, give comments.
What time?
It's up to you.
You are
The limit is the train.
So do not forget that we have a lot of 8 o'clock.
The job is 10 p.m. Okay, thank you for your work and for your very nice presentation. It was very clear.
Thank you.
I have to use the microphone. So thank you for your work and thank you for your presentation, which was very clear. I would like to start maybe, there's something for me which is a little bit surprising. It's your result with PDMS prism and sensor. Have you already checked what is the polarization of the beam after reflection on the sensor?
Yes, we could.
You have a polarizer at the entrance, but you have no.
We don't have a polarizer at the exit.
Yeah, of course. But do you check? Have you checked the polarization there? I mean,
but we could see that.
So I'm quite sure that you have a polarizer in the input beam, which means that you are TM.
Yeah.
You start with TM, but then the light is propagating into the PDMS, and when I see your curves with a quite low resonance peak, or sometimes no resonance peak, Have you any idea of what could be a problem of birefringence?
Actually, birefringence problem, as we could measure the air plasmon, where if the polarization changes, we could also see some changes. We don't see any changes in the air plasmon that was measured, but the problem comes only with the water plasmon.
Yes, but you explained and you say very clearly what was the geometry difference between the air plasmon and the water plasmon. Could you tell us what was the difference?
The resonance angle?
Yes.
Yeah.
The angle is much more
raising,
yes. Raising incidence. So if there is any birefringence, it's probably amplified since you are at the grazing angle. And it would be, well, that might be something. I'm not sure, but and especially you have problem. The worst case is the problem when you have a PDMS sensor 2, the second case in the middle.
Yeah.
You have never tried to measure some birefringence inside the PDMS?
During this work, we have not measured the birefringence.
It could be interesting, I'm not sure, but I've seen in the literature that they explain that it can exist, especially stress birefringence.
With the polymers.
Yeah, of course there can be some stress during the curing and there can be some annealing process to try to reduce it, I don't know. But that, I don't mean it's a solution, but that's something you should look at just to be sure that it is or not a problem. Okay, that's one thing. So if I have time for another question. You make the modeling of the plasmon resonance based on gold or gold and silver, and then you say that you used some quite thin titanium layer.
Yes.
Did you take into account that layer during the modeling?
Yes, but 2 nanometers of titanium was taken into account as a bonding layer between the substrate and the metal.
And concerning the metallic system using silver and gold, you made all the simulation with 5 nanometer gold because you explained clearly that was quite optimal result.
Yes.
But have you any idea how behave the 5 nanometer gold layer? Is it dense? Is it porous? 10 nanometer is very thin.
Yeah, 5 nanometers is thin, but we also have during the evaporation process to control the thickness of the metal is very difficult. So we say 5 nanometers, but it could be around 6 or 7 nanometers. Then we also see in our we matched the experimental result by increasing the thickness of gold, and we saw it was around it was not 5 nanometers, but it was 7 or 8 nanometers to match with the experimentally measured plasmon. But of course, by using 5 nanometers, it should be so porous, and oxidation can happen.
Yeah, that's a problem
yes.
I wanted to mention.
Yes.
And so, based on that, have you remeasured the plasmon a few weeks or a few months later?
Yeah.
To see if there is any oxidation on the sensor? And you see a difference?
Actually, the sensors are still here, but till now we don't have the oxidation effect for the moment, but it was covered by a PDMS. But of course, there should be oxidation. I think there should be some oxidation after a few days.
But you didn't make any SEM or AFM pictures of that, just to see whether it's really porous or just to see what is the surface.
Actually, the SEM was used to measure the thickness of bimetallic layer, but we could see we could not compare which thickness was what from the image that we obtained from SEM.
Okay.
So when we see the cross section, we deposited on the silicon wafer, and we saw the cross section from gold, silver and gold, and the comparison between silver and gold was not feasible.
Okay. Another question. But maybe just the detail, but on page 73, go there too. This was the thermal modeling. Yeah, you said that a heat transfer coefficient value of 50 has been taken, which is commonly used for laboratory condition. I'm a specialist in this kind of simulation, but what does it mean, a heat transfer coefficient of 50?
The heat transfer coefficient, it is it's like the temperature exchange from where we heat and to the environment. Okay. So we have air as on the surface of the metal. So how much heat is transferred to air? Okay. So for that we take a temperature heat transfer coefficient, which is around 50 for the air as an environment.
And is a coefficient without any units? It's normal? I don't know, just a question. I don't know how it is defined. So if there is no unit there, it's 50? I don't know.
It's what per meter? I think.
Just for my knowledge.
Yeah. What, so should be what per meter or something? I'm not sure.
Maybe one more question? Or?
Yes,
yeah, when you explain that I really like what you explained about the way to use a kind of internal heater and regulate the temperature. Then you explained also that you have this platinum resistor, but I was wondering whether there is not a crosstalk between the fact that you want to regulate the temperature and that you measure the resistivity at the same time. And the resistor, by definition, you have to inject some current and then you measure the resistivity. So when you measure it, don't you interfere, I would say, with the thermal regulation that you want to do?
No, to measure the platinum resistor, yeah, we use a very small current to measure the resistance.
How much compared to the current you need?
It's 1 milliampere was used to measure the resistance of platinum. And we saw under thermal camera there was no temperature rise for this particular current.
Okay, thank you.
So,
thank you.
Thank you.
Thank you, Professor Brickman. So now the word is to Professor Gilles.
Thank you. Thank you for your presentation.
Thank you so much.
Clear presentation. I would like maybe first to thank the supervisors, and especially Jean-Pierre, for giving me the opportunity to review this work. It was interesting because I am also director of a joint lab with a company. We are trying to develop industry of foil, and one of the application, plastic foil, and one of the application potentially could be sensing, especially plasmonics. So I was about to think about metallizing plastic type of foil and see the response. So when I received a PhD, of course, I was very, very interested in the topic. As far as your presentation is concerned, so I like the introduction where you remind us about the pathogens and so on. I found a little bit a pity that you did not place a little bit more your work in the context, the state-of-the-art context. And you did that, by the way, very nicely in your PhD. So if you don't mind, although this is a defense, I would like to have questions about the fact, one of the tables you have in the manuscript, where you summarize all the different techniques in order to do biosensing. This is page 8. Very interesting. They are mechanical, electrical, optical, but optical we only have SPR. There are many, many other.
Yeah, we have.
So why you didn't choose those other techniques, just having SPR as an optical technique for biosensing?
So the other techniques, which is also shown in page 4, we mentioned the different techniques from a reference, where in optical we have SPR, SMR, and MRR, they also use, but here I just compared what is the sensitivity or the minimum bit of detection that compared to other mechanical and electrical devices. Just
it would have been nice to have it here as well, because this table is very interesting. That's kind of, since your PhD is in English, maybe maybe someone may refer to this PhD and to the table. So I think if you have a chance, maybe it's not a lot of work to add these limit of sensitivity also in this case would be I think, very interesting. One thing also I really appreciate today is that you presented all the different partners. Whereas when I was reading, and especially the introduction in the manuscript, it was the other partners were not mentioned. So, or maybe I missed it. But anyway, so when I saw the Interreg program, it was about, with whom they do work. And here today you did it. So that's, please remember that.
Okay.
Presenting always all the different partners. And since we are about the presentation, I just want to also, was a bit annoying here when I saw the graph. It's a little thing, but again, maybe you can change this in the future. When you show experimental points, just show points. And when you show theoretical curve, just show lines.
Okay.
Because here you use both points, lines for both of them, and we don't know. It's difficult to know what is the theory or what is the experiment.
Okay.
So it's just an advice, but again, usually when we read a paper, it's easier to you understand what I mean?
Yes, yes.
For example, you have many curves where we see the sensitivity, for example. So the points are points, the experimental points are points, and then okay. Okay, so let me now have a couple of questions. I had the same remark about the birefringence, so I think it was maybe one of the key issues here to explain the results. Why the curve is missing here, about the PDMS and the polarization sensitivity, of course. I would have some other questions, but maybe I will come back later on that. I just have to remember page 36 here. So, for your measurements, okay, sorry. Another point is, you use the word propagative surface plasmons. There is no propagative surface plasmons. Per definition, plasmons always attenuate. So, I mean, it's, I understand this. If you talk to elder people, they may be shocked when you say propagative plasmons. Again, it's not a propagative wave. The intensity always decreases. I can say, tomorrow I can send you an email. It's just okay. Mark that.
Thank you so much.
I got confused, but I guess in the system, this is an hemispherical lens that is used. It's not a prism, in fact. Or in the system, is it a prism or is it hemispherical lens that is used?
It's a semi-spherical prism.
Semi-spherical lens, or let's say symmetrical lens. It is a semi-spherical.
Yeah.
Okay. Okay. Now, your first part was quite interesting about the theoretical analysis, I would say, except that you said that the system was developed already before, or the particle system exists before you start working on it. Right? What was used in that case for the first experiments? What was the experimental condition for the surface plasma? Well, there was no surface plasma.
So only the optical setup was existing as parts.
Okay.
So this was arranged and completely the measurements were completely started from the beginning. From the start.
So nobody did measure any plasma resonance before you did?
No, this was measured. Plasma was measured, but it was newly measured by using different sensors during my work.
Okay, and what was the previous sensor that were used?
That was gold.
Gold.
Yeah.
With no optimization? What was the thickness?
Actually, it was also silver gold was also done by PhD person who worked on it.
Okay.
This is was also using silver gold, but the thickness optimization was not done, I think.
Okay, so for the system, when you talk about the monochromatic, or let's say angular dependence interrogation, it's always infrared that is used?
Yes, we use 1550 millimeters.
Okay. In your work, did you try to use other wavelengths? And of course, what I want to say, did you try to use other wavelengths with different dielectric values for the code? For example, experimentally, usually this is a red light that is used.
Yeah.
So how would you compare in terms of sensitivity, your results with visible measurements for the monochromatic, for the angular interrogation? Have you done that?
Yes, actually, so we could see that the sensitivity that was measured with various thickness of the metal for various wavelengths, we could see the sensitivity is almost constant for higher wavelengths from 750 to 1500. But the sensitivity changes a lot depending on the thickness in the visible region from 500 to 700 nanometers.
So you see here typically it would be better to put points.
Points, yes.
Okay, so so you confirm that of course in the red the sensitivity is better.
Yes.
Okay, good. And as for the spectral interrogation, then it was done in the visible, with
yes,
white lamp.
With white lamp.
And of course in your modeling you take that into account. That's
yes.
for the dielectric function.
Yes.
Still about the sensitivity, did you look at also the intensity variation? You mentioned about the shift in angle or the shift in wavelengths. What about the intensity? Have you tried to compare? Because one possibility is also to measure always at the same angle and then to see the decrease in the signal because the curve is shifting.
Yes. So during the experiment, the angle was fixed when we measured the sensitivity for various concentrations of ethyl glycol.
It was fixed, okay.
The angle was fixed.
Okay, so then it's okay.
We see the shift in the wavelength. So the plasmon resonance was, the intensity was almost same for the concentrations that we used.
Well, what did you measure? You measured the spectrum?
We measured the, shift in the spectrum.
So you measure the shift in the spectrum, in the wavelengths?
Yes.
This I agree. When you are doing the angular interrogation,
oh, angular, okay.
Yeah, why not also measuring the intensity at one angle only?
Because in angular interrogation, when we fix the angle, we also fix the polarization and we see the maximum intensity. For example, in TE mode, we will be having a maximum intensity where we don't have plasmon. And then the image was normalized.
Yeah.
So when the image is normalized, we can the intensity change was not measurable because it's not.
I think this is what Gilles is mentioning, is what we call slope.
Slope follow. Slope follow. We also did, yes.
What about the sensitivity in this case? Did you try to see if the change is larger in terms of intensity compared to the shift to the change in angle?
Slope was measured, but as the slope depends on the limits that you take in the calculations in the software, it changes a lot depending on the limits that we take during the experiment.
The slope is not changing.
The slope is the intensity changes.
Intensity changes.
Yes.
So that might
we did not measure.
You didn't measure?
Yeah. The
you
intensity
still have
was
the
measured,
data?
but here it's not true. Yeah.
You still have the data?
Yeah.
You still have the data?
Data, yes.
Would be interesting to look at because usually it's more sensitive. So you get the change is larger as to compare with the angle. Okay.
Yeah. But yeah, it is also depending actually. We could try to measure this intensity by taking into account where we wanted to measure the intensity in the software, for example. But when we, it depends on the calculation that is made to measure the intensity also.
No, but you can simply imagine you measure your resonance and you fix at a given angle and you look at the change of different concentration. You will see the change in the intensity, of course, because your curve is shifting.
Can I?
Yeah, sure.
Yeah, there is, we understand what you mean, and I agree with you fully, because looking only at the shift in angle is not very sensitive compared to being in somewhere in the slope and looking at the intensity variation. But also there is another way to do, is to have a complete fit of the curve and compare with the new fit which is resulting from a delta L. And this is probably more sensitive again. So I don't know exactly what you use. So you look only at the angular shift of the peak, or at a new modelization of the full curve, the best fitting of the full curve with another M, refracting index. What are you doing exactly?
So we follow three things in the software. One is following the minimum shift, which is based on the calculation of centroid, and other is following the intensity, which is the slope, and also we follow the integration that is between one curve and another curve.
Yes. That's probably what I mean by a complete fitting
Yeah,
of the curve, looking for the best fit of the full curve with a new value of the refractive index, which means that you are really looking at every variation, not only the peak shift or not only the slope, but really having a real new curve coming from a new value of the refractive index.
I had a couple of more questions, a few more questions. You mentioned somewhere about the noise level, and you say 0.028 pixel. I was a little bit astonished by this value. So can you tell me a little bit more about? Sorry, I can't remember where it is. I noticed it somewhere.
It should be in the conclusion as well as in the...
No, it's a curve. It's the page 60.
In the view, yeah.
Page 6. No, it's not 0. It's noise level of the system. It's figure 3.11. 60. 60. 60.
Yes.
And you say the noise level can be evaluated at 0.028 pixel.
So, yeah. So here during the experiment, we measure the noise of water flow or whatever liquid we use. In the angular propagation scheme, we use image processing.
Okay.
So we see the noise which is in pixels. So it can be noise in percentage actually, not in pixels, but
you should
yeah.
Maybe percentage pixel. It's strange to read that. But that's the thing, and I really this is quite interesting again when you address the noise as for the limit of detection. In fact, the conclusion, right, where you say that you have higher sensitivity but lower limit of detection. This is page 145, 145. Well, this is what you also showed during your presentation. So, of course, having the two is important.
Yes.
It's coming back to this, the tape sensor, I was very interested in this one. What is the tape you use?
So here, the tape substrate was from 3M. We specially ordered a tape which is having a refractive index of 1.4 or something.
Yeah.
So it's a normal tape. A tape which is one side blue.
There is one side blue.
Yes.
Yeah.
But when we wanted to fix on the PDMS prism, we could see that we remove the polymer for the sticking, that is the glue, and we use only the tape, which can be directly fixed on the surface without using matching index or glue.
That's right, but still you may have a little refractive index difference.
Yes.
And this is about the spectra you show at the end, where you have all the different resonance curves. And there is one clearly where we see fringes in it. This is, I think, the red one.
Interference.
Well, yeah. You try to measure the spacing between the fringes and interferences, and try to get where these fringes are coming.
Sorry.
I think it was the last page 36. Yeah, this one. Yeah, on the bottom left, on the bottom right. Excuse me. So we see the interference here.
Yeah.
So those are interferences, Fabry-Perot interferences.
Mm-hmm.
You know where they're coming from?
This can be due that at the beginning when we place the tape on the surface of prism, because the prism, even we clean properly, it attracts dust very fast. So when we put the tape on the surface, maybe there is some gap between the surface of the prism and the tape, and it can be due to not proper matching of the tape and the prism surface.
It can be due to that, or it can be due to the thickness of the tape.
Yeah.
What is the thickness of the tape?
So here it's 50 microns.
50 microns?
Yeah.
I think I did, maybe I don't remember if I put it in the report, but I did some calculation. It's simple, of course. Calculation. 50 was not okay. I think 50 is too much. You will have more fringes. So I think it's right. You're right. It's coming from the kind of air gap, but I think it's also simply because of the glue, and you don't press, obviously.
Yes.
So of course, I do not expect the glue. Is like a rough layer. So I do not expect, of course, the glue to feel.
But here we don't use glue.
But there is glue on your tape, no?
No. The glue has been removed. We use only the tape, which is of the plastic.
Without any
polymer. That is without any glue.
Okay. But then it's strange, because then you will have only a very maybe 1 micron air gap or something like this. Whereas here it seems that you have more fringes than 1 micron, definitively more than this. So it would be just nice to try it, with a Fabry-Perot, you just calculate the spacing. Because we see, by the way, also on the left side, you see, we see the same.
Yeah.
We see the same. The contrast is just less, but we see the same. Okay. Okay, so I will be almost done. Of course, I won't say anything about but it's very important, the inbuilt temperature control. It's quite amazing, what you achieve. Maybe a question about that is to regulate the temperature, but it's also because you want to do outdoor analysis?
Yes.
Or it was one of the reasons why you want
Yes, as it's a portable system.
Portable system, yeah.
We need to
So you want to make sure.
Yes, the temperature what is in the place where it is going to be measured.
And about the perspective you mentioned about the surface functionalization, so you did try with surface functionalization? Did you try, or you just...
in our project, there is...
You yourself, I mean, in your
The
PhD.
surface no. I did not work on the surface functionalization.
But some tries have been already done, or with a functionalized substrate in order to detect the...
Yes, it has to be... it has to be tried with a biological solution. To heat the biological solution.
Yeah, and I had a very last comment is about the fact that you come back to the experimental refractive index. That is a bit also what is missing here. You, or maybe I'm wrong, but you try obviously to measure the refractive index of your films. Or did you? So like by ellipsometry, 5 nanometers is easy to measure by ellipsometry. Just to make sure that the refractive index you are taking into account, is the right one. Because for sure, 5 nanometers, it's a porous layer, won't be a full layer. So of course the refractive index is different. And not only because of the oxidation, and oxidation for gold, you know, I think it's a big issue. For silver, sulfurization, or some other things, yes. But so it would be interesting to simply do, you know, measure the index by ipsometry or direct transmission. By the way, direct transmission is also a very sensitive technique. If you have between 5 or 10 nanometers, you won't measure the same thing at all. So that will just maybe help a little bit improving the matching. So, and maybe the curve on the left, right, why is it constant at some point? Why do you have something flat? This annoyed me. You were discussing, and you said, I measure the resonance, but...
yeah, so, yes, actually here we don't use a density filter.
Okay.
So, full intensity of light.
Yeah.
When we measure the plasmon, we have to use a density filter to reduce the intensity. So here the intensity of light is too much.
But where is the resonance here?
So the resonance is here.
Okay.
The problem is the normalization is not correct.
Yes,
the normalization is correct for all the other curves because you're normalized to one maximum, but here we have no maximum.
We have no maximum.
You separated it.
You compare apple and pie.
Yeah, that's right. Okay. Thank you again for your work.
Thank you so much.
Thank you, Mr. Rondel, for this very interesting discussion. And now we will go through the partner, the digital partner.
Thank you, Siva, for the nice presentation. I have a few questions as well. Oh, maybe the microphone. Yes, especially with the mask. It's good. Let it stay there, okay. So the first question goes on the state of the art, actually. You know that the picture on page 4 that was already mentioned, there is a comparison between the microring resonator and the SPR sensor. And I'm surprised to see that the microring resonator has a longer analysis time.
Yes.
Do you know why it would be the case, or it was maybe specific to the publication?
Actually, here this is specific to the protein detection.
Right.
So this is the reason. It's because it's specific to the molecules. Here they use protein.
And why in the case of micro resonator that would be slower?
It depends on the interaction of the molecules. So here they use protein. I don't know, maybe the protein interaction time takes much higher, or because this is not a physical limit of detection. It depends on it's a dynamic range of the molecules as shown in this publication.
So it's probably linked to the biology.
Yeah.
And probably not to the sensor.
Not to the sensor, yeah.
Because from what I think, an SPR or micro resonator should have the same speed. Because so. Yeah, that was just a detail. Now, on the modeling, so you've done a lot of modeling, but for me it's not so clear what kind of modelization framework you've used. Have you used a transfer matrix method somewhere?
No,
have you used, what kind of dispersion curves have you used for gold or other materials?
We use group model for various reflection from different optical interfaces.
Right.
So the Selmayr equation was used to model.
So you did just a 2-stack model?
Yeah, 2 or 3 stack model.
2 or 3-stack model.
For various, the prism was taken into account and the thickness of the substrate and the titanium gold and silver gold.
Okay. And what kind of dispersion curves did you use for the metal? Because when we do the simulation in the lab, so we use the matrix transfer method, but depending on the gold model we use, we can have very different position of the plasma. And so I was wondering what model you used.
I used the basic multi-layer reflection model.
But I mean for the index of refraction of gold. Index of refraction as a function of frequency.
From Prout model.
Okay, so you just use a resonate with some resonator parameter.
Yes.
And that fits good enough.
Yeah.
So you had maybe to adapt the resonator parameter?
Here it was not adapted, but it could be adapted in future.
Okay.
It's not resonant. It's not resonant. You use a drill model.
Drill model.
It's a simple drill model.
Yeah. But I think that's
there is a plasma frequency.
yes,
Of course, there is a
that's what
plasma frequency.
that's what I mean. Depending where you choose it, they have a lot of differences.
We are back to the story of the radioactive index.
Yes. Then it's on the image processing in the angular model. I mean, there is a lot of horizontal lines alternating bright and dark lines, and I guess you use only a single line to have the plasma, right?
No, we take into account the average of the plasma.
Okay, right.
So we take image averaging on the area that we choose.
And I see on the image that the shape of the plasma is like,
yes,
there's a kind of coma shape. And does that enlarge the final?
This enlarges, it depends on when we use matching index to put the sensor surface. Whenever we use the pressing or not pressing, it depends a lot for measuring the plasma. It can shift just by not having good matching between the sensor and the glass. We saw this problem.
But so at the moment, you just integrate vertically, and that's what you do.
That's we do, yeah.
And you think there is a room for improvement?
Yes, it can be improved. So here also we said that some type of substrates that can be used where we do not need to use the matching index. So it can also improve. Matching index, it has to be properly fixed, or something has to be put tight on the surface of the prism for the better measurement. Because there is the gap between the oil and the prism. If it's not fixed properly, then we can have.
But my question rather goes on the image processing itself. Do you think there is room for improvements, so just managing the image more?
Yes,
in detail,
we can reduce. Yeah,
that you could actually improve the reading, and therefore the limit of detection.
We could improve the image treatment.
Yes.
Okay.
So it goes to my next question then. I still don't know what would be the best to implement in the end. Is it the angular system? Is it the spectral system? Because at the moment you show that the angular system is a bit better, factor of 3.
Yes.
Which is already quite nice. But is this difference between the two systems? Is it intrinsic? Angular will always be better than spectral, or it's just due to some different processing in one case or the other, and in the end we don't know which one will be the best?
Actually, it depends. The angular interrogation is better than by using higher wavelengths, as far as we saw. In the spectral interrogation, it depends on the treatment of the curve. It depends on the both, but the sensitivity improvement was higher when we saw in the angular interrogation by using higher wavelengths.
So it's mainly due to that?
Yes.
It's mainly due to wavelengths?
Yeah.
Okay. So we would have the same result for the same wavelength?
More or less, yes.
Yeah. You don't think there is a better choice?
The better choice is to use higher wavelengths.
Yes. For a given wavelength, you think that both methods would give similar results?
Yes.
Yeah, based on
there should be
okay. And then still regarding the comparison of both methods, at the moment we only see one plasmon in your image. I think you can go up to two, maybe more.
We can go up to 4 plasmons in the same image.
Yeah.
So the optical system was adapted to read 4 plasmons at the same time.
And you have to enlarge.
We have to enlarge the beam to expand the input beam.
Yeah.
And also it has to be parallel. And we focus on the 4 channels at the same time.
Right. And you think you could upgrade, for instance, to 12 channels or even more using a standard camera?
I think it's little, because even for 4 channels it was little complex.
Yeah.
Because beam expansion it's not, because the prism was also there, we should not go beyond the prism of focusing the line.
Right.
But it could be possible, but it depends on the sensor fabrication also.
Yeah.
If we have channels very close to each other, we could have 12 channels.
And could you imagine to have like a 2D map with the imaging system? Or that would not work?
It can work, yeah, to be, but
so you don't think it would be that easy to do? Yeah.
Yes, it's possible to do, and it could also improve for sure.
Yeah,
by using the.
Okay. On the temperature control, I was wondering what would it be useful for? I understand if it's high temperature, you could regenerate the sensor maybe when you use DNA, or do you want to use it to stabilize the temperature in order to decrease the LOD? What could be the different use of using this temperature control?
The temperature, as we saw, the refractive index of water was very hugely depending on the temperature. So now it becomes the temperature is also necessary to measure something that is real. For example, if we are measuring water, but we do not know the temperature, but we don't know which refractive index that we used at 20 degrees or 30. If it is a portable system, if we take from here and if we measure in some other place, if the temperature is different, we may have two different results. So in order, if we maintain the temperature and measure in the same different places, it has to be measured at the same refractive index.
Okay.
And also for the biological solutions, the temperature acts as a catalyst for the binding, for binding of different molecules. So it is also useful there.
Okay. So, because since for biosensing we work with relative readings,
yes.
Basically, so the absolute temperature is not that important between one place to another, I would say, except if you have maybe 20-degree difference, that might become important. But for usual condition, it's not so important to have the same temperature. Now, do you think that if we really want to decrease the LOD to the very minimum, do you think it would be able to control the temperature within 0.1 degrees C or even below that?
It is possible to control the temperature for because we saw it was shown that we could maintain 0.5 degrees and 0.1. It is in the noise level of the experiment, right? So it should be a little difficult to control 0.1 degrees, but
yeah,
I have to try to check if it's possible.
But you didn't try that configuration. That was not the purpose.
No.
Right? Yeah. Okay. Yeah, I think that's it. It was all the questions for the PDMS have already been discussed by reference and glue and porosity. I don't know. So that would be very interesting. I would be very interested to know what goes wrong with this. Because that's a very promising work to lower the cost of the system of the sensor. Yeah, thank you. That was my last question. My last comment.
Thank you. So maybe now we will work to your supervisors and we begin with Sophie.
Thank you, Siva, for your presentation. I won't ask a question today because I already asked a lot for 3 years. So thank you.
Thank you so much.
Thank you, Sophie. Maybe some comment from here?
Okay. So effectively, this is the end of your thesis, Siva. And it was a pleasure to work with you because, you know, a lot of time I asked you, are you sure of your results? Say yes, and then again another one to be effectively sure. And I do not know how many measurements you did, but it's a lot. Effectively, it doesn't appear in your manuscript because there is no error bars. But I think should be a nice, should have been a nice issue to put them because you did a lot of measurements. So I think the error bars should give a nice overview of the system. Okay. I think effectively you developed several. At the beginning, effectively, your only work was focused on the temperature measurement. But you said, okay, if we can use a polymer, it could be fine. And you also developed these innovative things using polymers as prism or as sensors. Right now, effectively, there is more question than answers, but it's beginning. Yes. And it was nice, effectively, to show your interest developing always new things with sometimes tricky ways to handle them, but it was funny to see how you manage this achievement. I have no more things to say. I think I already said you a lot of things, asked you a lot of things. So it was a pleasure, as I said, to work with you during these 3 years. And I hope effectively everyone in the consortium was also happy to work with you, and in the lab and in the consortium of the direct project. So thanks again, and wish you the best for the next.
Thank you so much.
Thank you, Jean-Pierre. So it's my duty to conclude your presentation. I have not so many questions, because I have so many questions for now, but I was wondering why you have made the choice to work in intensity instead of phase at the beginning for the integration system. You have made a choice. You have said that we work with intensity and not the phase. Why is it?
So actually, phase information system, even to make a setup, is very complicated and it's very expensive also. But our aim of the project is to develop a portable system, so it could be useful to develop a system which is more easier than the complex optics and the expensive optics too. Because the phase has to be read and phase meters has to be taken into account. Yeah.
So it's just a question of cost.
Yes, cost and difficulties for building an instrument in a short time.
Okay. I have one question, but the answer to this question was about the number of channels. You say even in your manuscript, you always say 4 channels, 4 channels, 4 channels. Why 4 channels?
The 4 channels is for the biological purpose it was done. For example, in the biologists, they could use one as reference and one as a negative test and positive test, and to compare each other. They use the 4 channels, or the 3 channels are important for biological measurements. First, to have reference and to compare. And other additional channels, it's for other. We could do multiple biological interactions at the same time and to have the results in the real time.
So then the question behind it, what is the maximum number of channels that you can imagine to build without too executive cost? So what is the maximum number, either when you look at the complexity or the cost, what is the good number of channels?
For the moment, I could say 4 channels because I work with it. But in future, it could be improved. Multiple channels can be used, but again, the setup has to be upgraded for reading this. So, for example, in the portable tool, they use 4 channels, and they develop a spectrometer which can read 4 channels at the same time.
12.
12 also.
It can read 12 already.
It can read 12.
Different fiber, but you have to.
Yeah, so they can read 12.
So what about 12 channels?
Yes, it's possible if we use this the spectrometer. We could read.
I have a last question concerning your platinum resistor, your really platinum resistor. It is in the perspective. It's a
yes, it's in there.
But from your point of view, what is the effort, the budget to do that, to succeed in this realization of platinum resistor in build? What is the effort? From now, is it 6 months of work, 1 year, 2 years, 1 PhD, or?
Actually, for developing a platinum resistor, it was done in during my PhD work.
Yeah, but
in the last year.
You say in build, in the sensors.
Yes.
It's inbuilt for now.
So, as it was in the perspective, I couldn't catch. Maybe I missed the point there. Okay, so if there is no more question, I think you can conclude your presentation and we will deliberate. So in this room.
Yes.
So please, you are now free to drink a coffee or I don't know, and we deliberate together.
Okay, sure. For people who assist in video conference, so we shut off the webinar video link, and we will also shut off the YouTube link. We will put again the YouTube link for the deliberation, so maybe a quarter, half an hour.
Moi non plus. Faut demander à Siva. Oui.
So, I could just stop the YouTube live? Yes, you just stop it.
Hélène a visio.
C'est fait.
C'est fait.
C'est quand même complètement sans. Ce genre de choses, c'est à l'époque nazie, on aurait compris ce genre de partie va pas demander. C'est le jardin pour voir s'il y a des décors dans l'obscurité en fait, de craquer quoi. Des compter le nombre de personnes pour voir s'ils sont trop. Ah bon. Si on regarde la science-fiction à la fois nazie, ça mélangeait de.
Couverture thermique, on se voit depuis aussi.
Voilà, une couverture thermique qui s'en avait.
Il y a des couvertures surprises, c'est ça? Oui, les couvertures surprises, c'est vrai.
Je ne suis pas pour vous laisser être d'accord des mais je ne peux pas exagérer.
Bon, je vais essayer de faire une petite photo en même temps.
On va tous là, ça marche.
On va là-bas ou on va oublier comment?
Non, voilà.
Allez, vas-y.
La caméra est toute devant le fond.
C'est toi.
Donc ne tient pas par la main quand même.
Devant l'écran.
Ici. Ah, dans les.
Devant l'écran là.
Ah, l'écran là. Ouais, mais c'est du journée. Yeah.
Okay, so Mr. Siva Krishnan, Ganesan, before giving the result of the deliberation, I would like to give you a few words about the discussion we had. The committee really appreciates your presentation. That was very nice, very well documented, and dynamic, very dynamic, read. And we also appreciate the answers to the questions that were very relevant and very well commented on. So for all this reason, the committee decided to award you the degree of doctor in the University of Lille. So in the specialty, this is a long specialty, you are a specialist of electronic, microelectronic, nanoelectronics, and microwave. And for all of this, we want to congratulate you.
Thank you so much, all. I would like to thank you so much. A few words. I would like to thank you all, even in spite of COVID, you come across the broad border. Thank you so much for that. And I have to thank my supervisor Jean-Pierre and Sophie Manico for always being open for discussion. And for 3 years, it was like my family. And I thank all my team members of the team for assisting directly or indirectly, supporting a lot. And I also thank my parents for giving the opportunity. And I thank you all. Thank you again. I thank my friends also, friends and colleagues. Thank you. Thank you so much. And all the best for the next steps of your career. Thank you so much. Yes, sure. So here we have a PDMS prism and a tape sensor. Yes, so very nice. The roughness looks very nice. So it's a tape sensor.
It's a tape sensor with a
view.
Okay.
And here, a PDMS prism with the glass sensor, which was plasma corona and it stuck all time. Okay. We can remove this. Okay. And PDMS prism with PDMS sensor. So, okay. There's no blue. There's no blue. There's a contact PDMS by PDMS.
Do you mind if I...
Yeah, please. And here is the tape sensor with 4 channels.
On va prendre l'indice de répartie directe.
Les assesseurs aussi à 5%.
C'est marrant, c'est on a le sentiment d'avoir un peu de rugueuse oreille, on a un effet lisse. Pour autant, quand on regarde à travers en transmission, ça semble. En fait, il est un peu rugueux. Et c'est évident qu'il est un peu rugueux. Donc ça, je pense que c'est peut-être ça qui fait perdre aussi un peu de directionnalité. Qui fait que ça voyait un peu. On voit bien par rapport au. En répétition, on voit pas bien. Mais bon, d'ailleurs, c'est joli, puisqu'ici, on voit que c'est brillant. Ça, c'est l'interface du bas. Là, on voit bien que la couche métallique est certainement. Mais bravo. Il y a les oranges, les couleurs rouges aussi, c'est un peu étonnant. Et après, c'est bien dehors, parce qu'on voit bien que c'est vert en transmission. Il n'y a pas de doute.
Yes, it was clean with the isopropanol.
With the isopropanol and PDMS, there is a reaction.
No, actually, we clean all the PDMS substrate or PDMS with isopropanol.
Yeah, but this one is hard. This one is hard.
Yeah.
So this one is soft.
Yes.
So it's not fully
polymerized.
So it may be that it's, I don't know, but it's strange that it looks so, or it's rough because of the coating. But anyway. Okay. And the tape is this one?
Yes.
So it's just a carton tape?
Non, c'est Rosen.
Yeah. Oh, sorry.
You shouldn't stick on me.
No, it won't be clean. But you have the same aspect, by the way. It also looks a bit rough as well. And here it's very, so, you see? The same.
We put directly on a glass substrate and we remove the top part and the glue sticks on the glass, and this tape removes without any glue. And here this is for platinum resistor with contact packs for measuring the resistance. And here is the normal the same sensor but with USB connectors. Wow. Directly USB connector. Yeah, on the side for measuring the resistance and also for nice technology.
L'empreinte que
this is the 4-channel sensor with microfluidics. And here is the tape sensor, which has the polymer in the base. There is the blue. This has 2 layers.
Okay. This has 2 layers. Okay, so there is a tape.
There is a glue.
Okay.
Siva?
Non, pas lui. C'est la caméra, elle est là. La caméra, elle est là.
Yeah. So,
J'ai une hésitation sur le système aujourd'hui. Je sais pas ce que j'ai. Avec une loupe de la j'aurais du mal de tourner à partir de chez moi. Ah oui, c'est vrai, j'avais pas pensé à ça. Et donc je vais montrer à JB qui est un collègue qui habite de mon coin et qui viendra avec Damien après les vacances. Après je reviens après. Ça sera tard, tu penses? Non, ça sera pas trop tard. Ouais, c'est ça. D'accord.
Schedule.
Ouais, je m'arrange.
Not sure it's something I was thinking with the presentation.
Ah, c'est génial, quoi. Et en termes de... C'était quoi votre
Au niveau du bruit, on a vraiment très stable. On a vraiment beaucoup de bruit, on remplace.
C'est le P2P ou c'est le
decrease the signal first. En fait, c'est d'un point à l'autre.
Ouais, c'est plutôt P2P.
Moi, je pense ça comme ça.
Ça va plutôt. On peut pas encore faire mieux.
Ça, c'est
non, c'est pas. Ouais,
c'est des vapeurs.
C'est
oui.
Si on avait des tablettations qui est plus étroit et
c'est les plus sensibles.
celui de 35 qui est un peu lié.
C'est l'IMS qui peut pas
Yes. On peut rentrer dans une biochimique.
Ah oui, you did the layer, j'ai ce
So we have a catalogue, and then we put the liquid PDMS, and on the top we put again a small layer of silicon to have 1 millimeter.
Oui, partout. Après, je vais
how to use your beam, and maybe some parts it's biofilter would be low, but not parts. It's just the transmiss which gain the
all our PDMS doesn't work, but all our PDMS work bien. Il faut que tu aies quoi comme système?
Il y a en fait des pentes construites sur la
ouais.
Je sens jamais là si tu as les lignes de la manette.
D'accord.
Le système physique par contre.
Le gros système physique, je sais pas. Parce que
c'est toujours comme j'ai en PDMS, je pense que ça va bien
ok, donc c'est juste par pression.
Et je suis en fait par rapport au...
Tu vois déjà comment ça se comment tu sais, tu vois une
de la réponse, j'arrête de serrer. Et là, j'ai un sens.
Parce que justement, si j'ai oublié d'apporter du passé avec un
en plus, je vais finir write it down somewhere. Et on est toujours en train de faire
Dans le système, en nouvelle vitesse de lecture, pouvoir moyenner problème je pense
Yes.
Il faut juste faire une chanson, mais après, il faut se
après, j'ai l'impression que
c'est jamais noir.
Je sais pas, c'est
Feel free to contact themselves. Okay,
Maintenant, au niveau de la sécurité, oui, parce que c'est pas possible. We can have a small drink. Okay. Thank you so much. And so let's have a small snack.
Yeah, Nikki, because
It's free.
very,
It's private.
Voiture qui a pas ici non plus un drone qui va survoler. C'est la salle du conseil.
Oui, j'ai envie de
Ils sont toujours en train de filmer. Ils sont toujours en train de filmer. La vidéo tourne toujours sur YouTube ou pas?
Oui, ça tourne sur YouTube, Siva.
Oh yes.
Il paraît
On va dire tout ça.